Hello everyone and welcome back. In the previous set of videos, we talked about big data, its characteristics, and also explained in detail the architecture of Hadoop in general and HDFS in detail. In this set of videos, we are going to get into the details of another core component of Hadoop called as MapReduce. Previously in our videos on HDFS, we have loaded a 1 GB file onto the Hadoop cluster, specifically onto the Hadoop distributed file system. The emails.txt file is divided into small chunks and spread across my cluster, like how it is illustrated here. This gives me the opportunity to process the data in parallel. But how do I do the processing? This is where MapReduce comes into picture. Before we get into MapReduce on Hadoop, I want to mention that MapReduce is a framework that was used originally by Google to process their huge datasets. After Google released a white paper on MapReduce in 2004, many implementations of MapReduce came into picture. Apache Hadoop is basically the most popular implementation of the MapReduce framework of Google. So what is MapReduce? MapReduce is basically a framework or programming paradigm that provides extremely fast and efficient parallel processing of data. Let us see how it does this. Conceptually and in general, any MapReduce program transforms lists of input data elements into lists of output data elements. And a MapReduce program will do this twice using two different functions. Firstly, the map, and then the reduce. The first phase of a MapReduce program is called map or mapping. This is the step where we simultaneously ask our cluster nodes to run a computation on their local block of data. The mapping phase will have an input list and an output list. A list of data elements are provided one at a time to the mapper, which transforms each element individually to an output data element. A mapping function or mapper may map one input into one output, or more than one output, or sometimes even zero outputs. Now, the second phase of a MapReduce program is called reduce or reducing. Reducing lets you aggregate or consolidate values together. Similar to the map phase, the reduce phase also has an input list and an output list. And the sorted output of the map function serves as the input for the reducer function, which then combines the values together, returning a single output value. This is, in general, how a MapReduce program works, irrespective of the language used to implement it. Now, getting back to Hadoop's implementation of MapReduce, firstly, let us take a look at what running MapReduce on Hadoop actually means. Just like in Hadoop distributed file system, where we have the name node as the master that controls and coordinates the storage function, for MapReduce we have the job tracker daemon that oversees and coordinates the parallel processing of data. The job tracker can run on the same server as the name node, or it can run separately as well. Here, let us consider that the job tracker is running on a server that is different from the name node. And similar to how we have data nodes running on the slave machines do all the low-level work of storing the data, we have task nodes running on all the slave machines that are responsible for doing the processing work as directed and controlled by the job tracker. Typically in a Hadoop cluster, as you can see, every slave node will run both the data node and the task tracker daemons. The Hadoop MapReduce framework takes the concepts of map and reduce and uses them to process large volumes of information. In MapReduce, no value stands on its own. Every value has a key associated with it. Keys identify related values, and the mapping and the reducing functions receive not just values but key value pairs. The output of each of these functions is the same. Both a key and a value must be emitted to the next list in the data flow. Now let us take an example to illustrate this. We have, let's say, an input file which has this text data. Remember, this example is just for illustration, so please ignore the simplicity of this example. Now we want to run a simple word count MapReduce program on this data and find out the number of times each word occurs here. So we pass this data to the first phase of the MapReduce program, which is the map. Remember, we said that the map and reduce functions do not receive just values, but they receive key value pairs. So when this data is sent to the map function, the Hadoop MapReduce framework splits the input data and sends it to the map function something like this. As you can see, each line in the input text file is considered a key value pair, where the key in this case is the row number of each line in the text file and the value is the sentence itself. Although the key in this case is the row number and does not make much sense, we still have to have a key since MapReduce deals with key value pairs. For the sake of explanation, just imagine that each line is sent to a different node in the cluster for processing. Now, the map function itself can have a simple logic to split each sentence into words and output the same as key value pairs. So the output of the mapper function will be something like this, where the key is the word itself and the value is 1, indicating that the word occurred once. Now the key here makes a bit more sense than in the previous phase, right? Here we are essentially finding a word in the map function and outputting a key value pair indicating that the word occurred once. A word can occur multiple times in the same sentence or in the same block of text being processed. So there will be multiple key value pairs being outputted for the same word. An example for that being the word king in the sentence being processed by node 1. Now that the map function has done its work, we need to aggregate the counts. But remember, since the word king could have occurred in any other mapper inputs as well, we need to ensure that all the occurrences of the key value pair for the key king should be sent to the same reducer. For this purpose, the Hadoop MapReduce framework shuffles and sorts the map outputs like this and sends this output to the various reducers. The reduce function in turn will aggregate the counts of the words based on the key, which is the word itself, and results in outputs like this. The output of the reducers will then be consolidated and stored back into HDFS files. Now that we have an idea of how a MapReduce program works, let us take our case study example and run a MapReduce job and see what happens in the Hadoop cluster. So to quickly recap, we are trying to find the number of occurrences of the words return, refund or exchange in the emails sent to the customer service department. We have already loaded the emails.txt file into our Hadoop cluster, and they now reside as small chunks or small blocks A, B, C, D, E on different nodes of the cluster. So now the client machine submits what we call a MapReduce job to the job tracker. Essentially, the client will provide the MapReduce job the programming logic for the word counting program, the input file path and the output paths where applicable. Since Hadoop is written in Java, the program will also be written in Java, although it can be very much written in other languages as well. And the program will be stored in a Java archive file or a jar file. So while submitting the MapReduce job, the client specifies the jar file to be used to run the job. In our case, when the client submits the MapReduce job, it is asking the job tracker, how many times do the words refund, return or exchange occurs in emails.txt. Now the job tracker in turn consults the name node to learn which data nodes have blocks of the file emails.txt. As we have seen before, the name node in turn checks its metadata and then returns the lists of data nodes that has the blocks of the file emails.txt. The job tracker then chooses the node on which the processing needs to happen. Remember, we have a task tracker running on the nodes of the cluster that does the processing. So the job tracker provides the selected task trackers with the Java code, that is the jar file required to execute the map computation on their local data of the blocks of the file emails.txt. Now the task tracker on those nodes start a map task, and they monitor the progress as well. The task tracker provides heartbeats and task status back to the job tracker. The logic of the map function itself is simple. It would be programmed such that it checks every word in the corresponding block of emails.txt that the map task would be running on to see if it is either refund, exchange, or return. If it is, then output the word as a key value pair like we saw in the previous slide, or else ignore that. As each map task completes, each node stores the results of its local computation in temporary local storage. This is called the intermediate data, and in our example it would consist of only the words refund, return, exchange as key value pairs. While the job tracker will always try to pick the nodes with local data for a map task, it may not always be able to do so. One reason for this might be that all of the nodes with local data already have too many other tasks running and cannot accept anymore. In such a scenario, the job tracker will consult the name node whose rack awareness knowledge can suggest other nodes in the same rack. The job tracker will assign the task to a node in the same rack, and when that node goes to find the data it needs, the name node will instruct it to grab the data from another node in its rack. Now the second phase of the MapReduce framework is called, as you already know it, reduce. The map task on the machines have been completed and they have generated the intermediate data. Now we need to gather all of this intermediate data to combine and consolidate for further processing such that we have one final result. When the MapReduce job starts, Hadoop, or specifically the job tracker, determines how many partitions the data will be divided into. This is done based on a variety of parameters that I'm not going to get into at this time. A single partition means all the intermediate data will be sent to the same reducer task. But based on the number of partitions required, the map tasks will assign each of its output key value pairs to a particular partition. In our example, there could be, say, two partitions, one for aggregating the word exchange and another for the words return or refund. The number of reducer tasks required will be approximately equal to the number of partitions. So in our example, the job tracker starts reducer tasks on two nodes. It instructs the reducer task to grab the intermediate data from all of the map tasks. So while the map tasks are in progress and the intermediate data is being generated, the reducer tasks start collecting the data it needs to reduce. After all the map tasks are complete, the reducers ensure that all the intermediate data is collected. Once the reducer task has collected all of the intermediate data from the map tasks, it can begin the final computation phase. The reducer function programming logic is also part of the jar file that has been provided by the client to the job tracker. The job tracker simply instructs the task trackers on the reducer nodes to just run the reducer function in the jar file. In this case, we are simply adding up the sum total occurrences of the word refund and writing the result to an output file. The output from the job is a file that is returned to HDFS following all of the processes we have already covered, that is splitting up of the file into blocks if it is greater than 64 MB, creation of a replication pipeline for those blocks, etc. Now when this process is complete, the client machine can read the output file from HDFS using visualization tools and derive insights out of it. This is basically the anatomy of a simple MapReduce program. You can extrapolate the same logic to more complex scenarios. Now we have seen how the MapReduce paradigm works. However, we have not seen how to trigger MapReduce jobs. One of the most common ways to trigger a MapReduce job is to run it manually from the command line on the client machine. A very simple format to run the job is shown here. Here you are invoking Hadoop and saying that you want to run a jar file called wordcount.jar, which has the logic to run the word counting program. You're also saying that the word count is the name of the class in the jar file that you want to execute, and the path of the input and the output file are also provided. Running this command initiates the sequence of steps we went through earlier. Remember that you can also write MapReduce programs in other languages such as C#, Python, R, etc., and not just restricted to Java. As you can see, MapReduce can process large datasets in parallel and generate results in quicker time than in traditional systems. There are a lot of improvements going on in the world of Apache Hadoop MapReduce, which will only make the framework faster and reliable. With that, we come to the end of this video, where we covered the architecture of MapReduce. In the next set of videos, we will briefly talk about the various projects that come under Hadoop, such as Pig, Hive, HBase, etc. Thank you for watching and stay tuned.